The first step in describing how a laser works is to answer the question, how do atoms respond to applied signals? By signals, we could mean an incoming electromagnetic wave, applied current, or really any force acting on the atom that wouldn't be there if the atom were by itself. It turns out we can derive the essential features of laser dynamics by using almost only classical physics. We'll start with the Lorentz oscillator model, or what some people call the classical electron oscillator model. Suppose we have a positively charged nucleus and a negatively charged electron that we conveniently both place on the x-axis. This could be the only electron in the atom, such as in the case of hydrogen, or it could be one of many, doesn't matter. In the Lorentz oscillator model, we approximate all the forces acting on the nucleus and electron as being due to a spring connecting the two, a spring constant K. We also call the distance between the nucleus and electron x of t. Suppose we apply the most familiar type of signal, an electric field pointing in the x direction that we call E of t. There will be two forces acting on the electron, a spring force given by negative k times x of t, and a force due to the electric field given by negative small e times big E, where negative small e is the charge of the electron. Using Newton's second law, we can write down the equation of motion. A more useful way of writing this is in terms of omega A, which is called the resonant frequency. This resonant frequency is incredibly important since it's equivalent to the transition frequency of a real quantum mechanical atom. At this point, it seems like we're done, but not yet. There's still one problem. If we solve the equation for the situation of no applied signal, meaning no electric field, we see that the electron oscillates forever. This can't be right. Our solution is to add what's called a damping term, which is gamma times dx dt. This gives a much more realistic solution in which the oscillations die out exponentially. Notice that the frequency of the oscillations has also changed, and we now call that omega A prime. In practical situations, however, omega A and omega A prime are about the same. From now on, to make life simpler, we'll just write omega A prime as omega A. Now it's time to address gamma. A start would be to write out the energy of the atom, assuming that the nucleus is too heavy to move significantly. There are two parts, the potential energy of the spring and the kinetic energy of the electron. If we plug in our expression for x of t, as well as its derivative, into our energy expression, we get that the energy is equal to the initial energy times e to the negative gamma t. Just to emphasize, this is only the energy of the electron oscillation. This doesn't count other sources of energy, such as the entire atom moving around. Since the energy decreases exponentially according to gamma, we call gamma the energy decay rate. How do atoms physically lose this energy though? There are two categories, radiative mechanisms and non-radiative mechanisms. Let's talk about radiative mechanisms first. Radiative mechanisms are exactly what they sound like. Both Lorentz oscillators and real atoms will lose energy by emitting electromagnetic radiation, but specifically radiation at the frequency omega A. Radiative mechanisms are exactly what they sound like. Both Lorentz oscillators and real atoms will lose energy by emitting electromagnetic radiation, but specifically radiation at the frequency omega A. As a side note, we'll use the terms resonant frequency and transition frequency interchangeably to refer to omega A. Non-radiative mechanisms are all the other ways that an atom can lose energy. This includes bumping into other atoms, emission of heat into a surrounding lattice, etc. To emphasize the distinction, we write gamma as two parts, a radiative part and a non-radiative part. We call gamma rad the radiative decay rate, and we call gamma nr the non-radiative decay rate. If you want to calculate these decay rates properly, you need quantum mechanics. However, you can also calculate these decay rates for the Lorentz oscillator, and the values are of the same order of magnitude. We've now finished introducing the classical model of the atom. In the next video, we'll calculate both the dipole moments and the polarizations due to these atoms, as well as introduce the concept of dephasing.